Hi everyone, my name is Ioannis Anifontakis. Welcome to a small video series regarding Introduction to Deep Learning Theory. In this first video, we will see just the introduction. We will see different types of neural networks and applications, but from the second video and on, we will see the actual theory and math behind deep neural networks. However, I encourage you to watch this video to the end as it will give you a solid foundation. Now, before we continue, I will also like to tell you why I am making this video series. Actually, I've seen that many people find it hard to get started with neural networks. It was a little bit hard for me at the beginning as well. So I tried to put everything in an easy to follow video series so that even those who are not related to neural networks in any way will find this video series a good starting point so that they start using neural networks and deep learning. Now, me as a developer, what made me start digging into deep learning was that there are certain things that I couldn't just do by code. I mean, let's take an apple, for example. Okay, apple, for example. Can you describe by code the shape of an apple, its texture, the color? I mean, if it's peeled, if it's cut in half, if it's half eaten, is it at a tree or is it at a plate? I mean, there are so many different pictures of apples that you can see, but how would you process them? I mean, you as a human can identify that this is an apple, but how can you ask a computer by writing code if then else statements to identify what an apple looks like, so that tells you I see an apple in this picture or not? So that's one of the things that made me want to look a little bit more into deep learning, as it does allow me to do things that I couldn't do with code alone. So now let's look into this apple thing. Now, from former experience to intelligence. Okay, what do we mean by that? Intelligence is based on conclusions. Now, in order to describe what an apple looks like, you already need to have seen a few apples in your life so that you know what an apple looks like, so that you can classify a fruit and say, yes, I see an apple, or I don't see an apple. Now, you have it, it's your natural intelligence. So you have it because you have seen many apples, and you can draw now conclusions when you see a picture based on the features that you see. So you see certain features in the picture and say, yes, I see an apple in that picture. Now, when we mimic the ways that we learn as humans, so when we mimic our natural intelligence, we in an artificial way, we perform artificial intelligence, okay? So we give birth to AI. Now, don't be so excited because no intelligence is perfect, right? I mean, mistakes happen every now and then, and I mean, that's totally fine because you make mistakes too. How many times have you seen something and have confused it to something else? So, neural networks won't be perfect. They will make very, very good estimations, but they won't be perfect, as you are not perfect either. For example, did you notice that the picture here at the lower right corner is not an apple? That's a peach, by the way, and here we are. You might have noticed it before I said it, or you might have missed it. It doesn't really matter if you saw it, because there are other people who might miss it. So by that we mean that nothing is perfect. You might have to take a second look, or you might didn't see that the picture was not very clear, and so on and so forth. So no intelligence is perfect. You make mistakes too. So that's what will happen from time to time with deep neural networks, and that's why that's because they are based on intelligence. They're based on conclusions drawn, and those conclusions might be wrong from time to time. Now, where is deep learning found? It's actually found everywhere. I mean, from informatics to entertainment. When, for example, in Netflix, you get recommendations about movies to watch, from medicine, when you scan for tumors in MRIs, for example. In automobile industry, when we talk about self-driving cars, even at your mobile phone, I mean, you're using AI all the time, even if you don't know it. Now, there are many different types of neural networks. I cannot put all of the different types of neural networks here, but there are some that are, the most, let's say, famous ones. Feed-forward neural networks are the ones that we're going to see. We start from perceptrons and we continue to feed-forward neural networks, dense neural networks. That's the multi-layer perceptrons that we're going to look. We will also, in this course, compare multi-layer perceptrons to convolutional neural networks, which excel when it comes to identifying pictures, classifying pictures. There's also recurrent neural networks, or RNNs, that we're not going to focus in this specific tutorial. However, as a brief intro, I will tell you that RNNs get the output and feed it again as input, sort of. So that's why they called recurrent, because the output becomes part of the next input. As you understand, this will allow you to get context that you don't have in other types of neural networks, and thus they are used in tasks like natural language understanding. LSTMs and GRUs are the evolution, let's say, of RNNs, as they deal with some problems that were found in traditional RNNs. As they introduce memory. RNNs don't have that good memory, but that's out of the scope of this discussion. Autoencoders is another type of neural networks. They are used in cases like compressing images or denoising images, where especially on denoising they're very, very useful and very good. Generative adversarial networks are the type of networks, the GANs, they are the type of networks that actually bring the artistic part of neural networks. They compete each other, so we have, let's say, a classifier and the generator, and the classifier will try to predict if the image that it sees is a real image or was produced by the generator. So the generator will have to get better so as to fool the classifier, until the classifier gets confused and believes that the generated image, for example, is a real image. And that way we say that those adversarial networks, those competitive between each other networks, are in balance. And this is the kind of networks that we use for drawing pictures, for example. All right. Now, there are three different basic categories when it comes to machine learning. We have supervised learning, reinforcement learning, and unsupervised learning. Supervised learning is all that this tutorial will be about, and the definitions come from they come from Wikipedia. So in supervised learning, the definition is that it's the task of learning a function that maps an input to an output based on example input-output pairs. So that in short means that we will train our neural network with labeled data, with data that we tell the neural network what it is, so it gets better into understanding this type of data. And when we introduce a new picture, let's say, of an apple, since we know that we have trained our neural network with 10,000 pictures of vegetables and fruits the neural network will be able to distinguish which one we refer to. Then we have unsupervised learning. Autoencoders that we talked earlier are part of unsupervised learning. In unsupervised learning, what it does, it helps find previously unknown patterns in data set without pre-existing labels. So it's training on data without labels. And one good example of unsupervised learning will be clustering, where we try to find differences between data that we don't know how they differ. Reinforcement learning is another big area. It's also out of the scope of this video series, but it is concerned with how software agents ought to take actions in an environment so as to maximize some notion of cumulative reward. And if that sounded a bit confusing, you will not be confused in the next few minutes, as I will give you examples in all those categories. Now, when it comes to unsupervised learning, clustering for example, let's say that we feed our neural network with few images, and it doesn't know anything about those images, but then surprisingly the neural network will, let's say, cluster them into two categories, as it was able to draw some conclusions based on which, let's say, it gave us a set of images of cartoons that have a bird beak, so ducks, compared to non-ducks. So even though it didn't know anything about ducks and non-ducks, it found some common characteristics, so it clustered the data set that we provided into two categories by itself. So that's unsupervised learning. Now, when it comes to supervised learning, one of the major categories is classification. And now in classification, I want to show you, for example, we give it a picture and it understands that there is a cat. Or we can also use localization and tell us where the cat is located. Also, we could have multiple types, multiple classes detected. So we say that we found cats, dogs, and ducks here. So we have two cats, as you see, two red rectangles here. So that's for detecting multiple objects. Or it can also draw shapes around these objects, which is actually segmentation. So it doesn't just show us where it is, but what's the shape of the detected item, which is very useful in cases like medicine. Now, this instant segmentation is something we're going to look again in the next slide, as to me it's very, very big. Here you see an example of, not an example, several examples of semantic segmentation when it comes to computer vision. As you can see in the upper left corner here, you see, for example, how it can be used in self-driving cars, where you can, where the computer can now understand what shape is what item. Also, the same thing you can see down here on the lower right corner, and let me clean this up. So here you see that we can detect humans from cars, from road, from plants, everything, road signs. So that's one big thing in when we talk about self-driving cars, but also imagine how this could be beneficial in cases like medicine, where you could scan an MRI and pinpoint possible cancers. All right. On the upper right corner, it's me with my wife. This is a very simple segmentation where it finds where humans exist in the picture. So you see that it drew a shape on top of us. Okay, so that's semantic segmentation, a very, very big thing when it comes to computer vision with Siemens. One other funny thing that I liked was style transfer. You know, it's one of the side effects, as I say, when it comes to combining pictures in neural networks, where you have one picture as your content, and this is Logia in Heraklion, the picture above in my city, and we also get the style from another picture. So what would happen if I combined the picture above with the style of the picture below? Well, that would be the result. So style transfer is another very nice and funny part when it comes to combining neural networks and producing images from that. One other big thing as well is deep reinforcement learning. Here, what you are going to watch is a video where we start playing Atari games, okay? The agent doesn't know anything, just sees pixels, and knows that you have to go right and left, and your goal is to maximize the score. In the beginning, it really doesn't know what to do, it just keeps losing. But by being training via trial and error, the agent becomes better and better. So in only 2 hours later, the agent plays like a professional. So as you see, by trial and error, where it gets rewards about positive outcomes and penalties for negative outcomes, the agent adapts in the environment. The amazing thing is, however, in another 2 hours, where the agent finds that there is a trick that it can do, that by digging a hole at one of the corners, it can let the ball do the work on your behalf, so you don't have to just chase the ball anymore and get high score like that. So that's deep reinforcement learning. It's adapting an agent to some environment, and we're going to see more of reinforcement learning here. Here you're going to look into a DeepMind application from Google, where an agent learns to walk into an environment. It might look goofy as it says here, but get the big picture of it. Alright, so we just saw how deep learning can be used to teach an agent to adapt to an environment. Now, this was all in software. What about when we put this now in our hardware and use it at a robot? The next application you're going to see is a real application on an existing robot, and I think you'll find very useful. Let's look at another application with 4 legs. So that was when it comes to making real applications with what an agent can be taught. Here we go to an entirely different subject. We go into looking at generative adversarial networks, the networks that I told you that compete each other. This is, you can see the link here. It's from my GitHub, from a project that I did at Udacity's Nano Degree for Deep Learning. It shows pictures generated by the neural network of faces. So all the faces that you see here belong to people that don't really exist. They are all drawn by a neural network. So this is quite amazing to see all those people, all these pictures of people that never really existed. So that's one of my projects when it came to my deep learning nano degree at Udacity. Another application is here, and it's, you can see the zebra generator. It's quite amazing how it was able to transform the left picture into the one on the right. It didn't just copy the features found in zebras, but it also copied the features found in the African grounds. I mean, you will see that the grass on the left looks more like an African ground now when it's on the right picture. So it looks like more like savanna. So that's another application done in with generative adversarial networks. Also generative adversarial networks, one other thing that I also liked very much, you can play with the link here at the bottom, where you can put any black and white picture and get it colorized. One of the funny and nice things that I found when it came to this was that if you see the picture on the left, this is actually a black and white picture from a black and white video clip from Prodigy. And the picture on the right, if you notice, I don't know if that was accidental, but what really surprised me was that it really had the flag colors of the United States. So, I mean, this shirt is blue and red, just like the colors of the American flag. So it was really amazing that this just happened by a neural network, and there was no real intelligence, no human intelligence colorizing the black and white picture into color here. But this was all done within a fraction of a second by a neural network. Another thing is, another nice application you can see here, the link, if you follow this, you will get to do what you see here on the left, where you just put, shapes of different colors, and the neural network will try to estimate a realistic picture based on your drawing on the left side. So that's also an amazing application you see here. Now let's leave a little bit the world of GANs and go into recurrent neural networks, here is yet another of the applications I did during my nano degree at Udacity with RNNs, the link of which you can find here. This is sentiment analysis. So we have an example here where you give a movie review, okay, and the neural network tries to predict if this review was a positive or negative review regarding this movie. So this is the outcome for a positive review that I wrote, and here you see the outcome for a negative review that I wrote. I mean, it's really intelligent. So you can now, for example, in IMDb, let's say, they will be able to know with such systems how positive some people are regarding some movie or not, without even rating it. Okay, so that's one thing. Now another thing, this is Google Duplex that we're going to look now. It's recurrent neural networks to the next level. I mean, I really don't know how they did this at Google, but I mean, this is the natural language understanding to the next level. Have a look.
What you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
How can I help you?
Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd.
Sure, give me 1 second. Sure, what time are you looking for around?
At 12 p.m.
We do not have a 12 p.m. available. The closest we have to that is a 1:15.
Do you have anything between 10 a.m. and 12 p.m.?
Depending on what service she would like. What service is she looking for?
Just a woman's haircut for now.
Okay, we have at 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
So that's the RNNs as well. Now, there are certain platforms that you can use to code your own neural networks. Two of the most widely used frameworks are TensorFlow on the left here, which is made by Google, and PyTorch here on the right, which is done by Facebook. They both have their pros and cons, however they are very similar. TensorFlow is older than PyTorch, so it's a little bit more mature when it comes to coding, but PyTorch is more widely used in academia. Now, when it comes to training your neural networks, you will see that CPU is not very good solution, because CPU is good at sequential data, but when we deal with thousands and thousands of weights that we need to alter and calculate, we need something that is better at parallel data. So GPUs and TPUs are better at processing parallel data. GPU stands for Graphics Processing Unit, and in deep learning we use mostly GPUs that have the CUDA interface. So we use the CUDA cores to train neural networks in parallel. With TPUs, where TPU stands for Tensor Processing Unit, they outperform GPUs. They are currently used only in TensorFlow, but PyTorch will adopt TPUs soon enough as well. So don't consider this, a deal breaker when it comes to learning PyTorch. Now, let's talk about CUDA. And let's talk about CUDA because you can use CUDA, as I said, to make training at your very own PC. So the laptop from which I'm recording this presentation runs the 960M GTX, which comes with 640 CUDA cores, so you can perform 640 calculations in parallel. Now, if you're on a desktop PC, the very same graphics card comes with almost double the CUDA core, so you can see the boost here. Now, I won't name all the values here, but you can see that up to a GTX 280 Ti that comes with 4,352 CUDA cores, you can do really amazing training very fast. Now, the last one, which is Tesla K80, that has about almost 5,000 CUDA cores, is what Google uses at Google Colaboratory, or Colab as we say, and which is free and you can use it. However, you won't get the performance of all 5,000 CUDA cores, as you will get just a portion of it, since you're running a virtual machine that cannot use all the hardware resources. I have found it that the performance I get from for free with the Tesla K80 at Colab is about similar to the 640 cores that I have in my 960M edition of CUDA in my laptop. Now, you can find more about this at the video link here. That is another video that I did about 6 months ago that is an introductory video to Colaboratory, and I believe you will find it very useful. It has all you need to get started with Colab, and it also talks into more detail about CUDA cores and GPUs. So, tomorrow is now. Get your hands dirty and start modeling. If you want to start working with machine learning and deep learning, I think a Colab is a very good start, as you need nothing but your Google Drive to get started, and you can just start working right away. If you want to use your own PC, you will need a PC with NVIDIA graphics card, preferably, so that you can boost your training. And you will need to install Anaconda or Miniconda. It's a very good way to start. You will be mostly working in Python, and you will write your code in what we call Jupyter Notebook. So I wish you good luck on your journey towards deep learning, and I will see you on the next video, which I hope I will shoot really short. Have a nice day.